All right, let's take care of this last explore. Explore number 3 of using vectors and scalars to describe motion. We'll go ahead and take care of our Cornell notes, draw our templates, write down the essential question we'd like to be thinking about. This is going to be guiding our note taking. That essential question is here in green. When a force is applied, to an object in a direction perpendicular to its motion. What are the effects on its speed and direction? Okay. So I want you to think for a moment. You're going to write down what you know, what I know, or think. Go ahead and hit pause and write down what you know or think about this question. Okay. Hopefully you took that time to write down what you know or think. Remember that perpendicular the symbol like this. If we were to say that I have a wall, this is a wall, then I could say that this second wall is coming in perpendicular. The red wall is perpendicular to the black wall. You could say the black wall is perpendicular to the red wall. What does that mean? It means that they are forming 90-degree angles. The angle between them is 90 degrees. Okay, that's the definition of perpendicular. Okay, so then by extension, if we were to say that you have examples of perpendicular examples, if you have a car and the car is moving in this direction and some other force comes in and pushes the car while the car is traveling. Maybe the car is traveling 60. Let's see what he said. Maybe the car is traveling 60 miles per hour, right? And you have another force that comes in and applies 100 newtons. What's going to happen to the car? How is it going to be affected? Will it change direction, right? And again, we're probably trying to show here three-dimensionally. This is a 90-degree angle. 90-degree angle, perpendicular. Okay. Well, now that we kind of just got our brains warmed up a little bit, and we were just thinking about that, right? The effects of force on magnitude and direction. The effects of forces on magnitude and direction. Okay. In this first paragraph, they talk about forces, unbalanced forces. If forces are unbalanced, they can cause changes in objects' velocity. And a change in an object's velocity is an acceleration, right? Review. If you recall, we had talked about how if you have a box and you have a something that's pulling with 2 newtons, and you have something that is pulling with 1 newton, then this produces an unbalanced force. This is going to result in the box moving, in this case, to the right. And remember, any change in an object's velocity, and velocity is a vector quantity. It's a either a change in it's your speed with a directional component, right? So unbalanced forces can result in this. An object that is already moving has a velocity vector with a direction and a non-zero magnitude. If a force acts on the object in a direction parallel to the velocity's magnitude changes. The direction of the velocity stays the same. Okay, so the second paragraph offers us just a slightly different insight. Okay, so let's first say here, capital A, unbalanced forces acting on an object result in changes to velocity, therefore changes to acceleration. Okay. And our example there was the box, right? You had the box that was pulling, a box that was pulling this direction. We said 2 newtons, we said 1 newton. So this was unbalanced, right? Now, how about this next scenario here, paragraph, the second paragraph there. What if you have an object, okay, close our object, and your object is moving in a particular direction, okay? If a force acts on the object in a direction parallel to the velocity, okay, so if this is moving, let's say at 10 meters per second, right? That's the velocity. And then something comes in and either moves it to the right or to the left, a parallel force in the same parallel force, that's so to speak, in the same axis of motion. What will be the result if you apply a force either to the right or to the left? Will it change direction? No, it won't change direction. Will it affect the speed? Yes, it will affect the magnitude, the speed. Okay. This won't affect direction, but does affect the magnitude. If it's pushing to the right, it'll move faster. If it's pushing to the left, it'll move slower. If force is to the right, it will move faster. And conversely, if the force is to the left, it will what? It'll slow down. Okay, so these were parallel force, right? This was a parallel force. It can either move parallel force, okay? Okay, so let's come back over here and let's just clear our screen and continue to move upwards here. Okay, so they give you an example. They give you several examples, and then the next paragraph down, what happens if two billiard balls, right? These are billiard balls, both in motion, collide with each other at an angle. What will be the effect on that? Well, you're right if you thought that it's going to change direction, right? And you'd also have been right if you said that their speeds would also be affected somehow. Okay. So that was an example where that would be a force that was not coming in parallel, right? Okay, so I think they're setting us up here. On the other hand, if the force on the moving object acts in a direction perpendicular to the velocity's direction changes and the magnitude of the velocity stays the same. Okay, so let's see here. Let's do this. Say letter C. And we could say that in letter C, you could have a ball that is moving in this direction, and it's going to collide with a ball that is moving in this direction. So what's going to happen to these balls when they collide? Well, the result might be that this ball is going to bounce off in this direction, and it's possible that this ball is going to bounce off in this direction, right? And so what you'd have in this example was changes in both velocity, we shouldn't say just velocity, changes in magnitude and direction occur, right? Now, the third example then was the one that was our original question. What happens if your object is moving in a direction? You've got we had the example of the, let's just say you have a satellite, okay? Let's call this a satellite. And we could say that the satellite is, here's Earth. Let's say the satellite is moving this direction. Okay. And let's just say that you have Earth underneath. We'll draw Earth. This is planet Earth. What would happen? This satellite would continue to move to the right unless some force acted upon it. In this case, we do have a perpendicular force. We have the force of gravity, right? Gravity pulls things to the center of Earth. So we could say that there is a force, right? The force of gravity is pulling this at a 90-degree angle, right? This is a 90-degree angle. Thanks. So what would be the effect on this? Would it change the direction of the satellite? Would it change the speed of the satellite? Or would it affect both? And as it says in your text, the velocity's direction would change. Okay, so the only change in this example would be the direction. Okay, and the speed would not change. In this case, direction changes, not speed. Again, I'm going to take the word speed out. We're just going to use the more general term, not magnitude, okay? And speed is a type of expression of magnitude. Magnitude, all right? Okay, so this brings us down to probably the last ideas here. This was uniform. This example that I gave you here actually was introducing you to uniform circular motion. Okay, so I think we need to go back up here and get that line and drop our line down here. What do you think? Okay. Okay, so this opened us up to the ideas of uniform circular motion. You could think of a Ferris wheel, i.e. a Ferris wheel, or you could even think of a carousel. I'm not really sure how you spell carousel, but if you're at the fair, you might have one of those large structures where they have those giant things that are circular, and you're sitting in one of the chairs, right? And these things spin around. Uniform circular motion. This is going to turn in a uniform circular motion, right? And in this uniform circular motion, there's a concept called centripetal force. Okay, there's some good videos in your text, but that show, for example, if you're driving a car and somebody is driving in a circle, and you can feel yourself wanting to be thrown out against a car, but the car door is kind of holding you in, or maybe your seatbelt is kind of holding you in and pulling you in. So the centripetal force is a force that is pulling you towards the center. Okay, so centripetal force. Centri meaning center, centripetal forces pull you to the center. Okay. And so when you take a look at our picture up here of the satellite, you could even say that the force of gravity would be a centripetal force. The force of gravity would be a centripetal force. It pulls the satellite to the center of Earth's mass, right? And so as that satellite goes around and around and around, it'll be constantly pulled to the center, okay? So if I were to kind of come over here, I could draw my planet, and I could draw my satellite going around and around and around. It would be going at the same constant speed, but it would be constantly wanting to be pulled in towards the middle, right? It's constantly being pulled in towards the middle, and at the same time, it's wanting to travel in a straight line. So it's going to just end up with this resultant circular orbit, okay? All right. So circular orbit is seen in this demonstration here, okay? So clear the screen, and did we take care of everything well, look at that. We did. So you know what you need to do now. That was nice to have a short one. Go ahead and draw me your summary, write me your summary paragraph. And that is it. You guys have a great day, all right? All right, talk to you soon. Bye-bye.